Okay, everyone, welcome back to part two, video lecture part two for chapter two um, on the chemical properties of life. If you recall, at the very end of the first video lecture for chapter two, we had just started discussing valence electrons, the outer shell electrons and atoms, and how they relate to a chemical or to an atom's reactivity. Remember, we said that the very first shell can hold 2 electrons, but any shells beyond that, 2, 3, 4, for example, can hold 8 electrons, and that's referring to what's called the octet rule. And we talked about that with regard to this figure, where as we go from left to right, the outer shell becomes more complete and the atoms become less reactive until we get over here to the noble gases on the right, helium, argon, neon, for example, that have complete shells and therefore don't react. So the valence electrons then are those in the outermost shell, and they broadly determine the chemical behavior of an atom. Elements with a full valence shell are referred to as being chemically inert. They do not react with anything. Okay, now these electrons then, excuse me, that we're referring to in the outer shell, the valence electrons, they're the ones that are involved in chemical reactions between atoms. And I said in the first part of this video lecture that atoms want to complete their outer shells because doing so makes them more stable. And that one of the ways that an atom can complete its outer shell is to bond to other atoms. And you'll recall that I said that the valence number is the number of electrons an atom is missing in its outermost shell that it would need to be complete, and that valence number therefore tells you how many bonds or chemical bonds the element or the atom of the element will form. Okay, so the thing is that all these electrons that are moving around the nucleus of the atom have a negative charge, so they all have the same charge. And here's a rule in chemistry: like charges repel each other. In the same way that opposite charges attract, similar charges or same charges repel each other. That means that electrons, while moving around the nucleus of the atom, want to stay as far away from each other as they possibly can because of the repulsive force between them, but they also need to stay around the nucleus and are therefore kept there by the opposite charge attraction between them and the protons in the nucleus. Now, you can imagine in your mind's eye that if you had a single electron like hydrogen, it would not have to repel or be repelled by any other electrons. So it could move in sort of a three-dimensional sphere around that nucleus wherever it wants to go. But throw in another electron. Now those two electrons repel each other, so maybe one kind of sets up shop on the right-hand side of the atom, or in one hemisphere, let's say, of the atom, the other sets up shop on the other hemisphere, and now they're kind of restricted. They can't just go anywhere. They repel each other, so they're restricted. Throw in another electron, or 2 more electrons, or 5 more electrons, and you would see that the situation would become more complex, with electrons being restricted to ever smaller volumes of space around that nucleus. These volumes of space where we find these electrons are called orbitals. So an orbital is the three-dimensional space around the nucleus of an atom where an electron is found 90 or 95% of the time, okay? And each electron shell consists of a specific number of orbitals because each electron shell can hold a certain number of electrons. Now, the important point here about orbitals is that the orbitals are the locations of the electrons. And as we'll see in a little bit, with bonding, where the electrons are located around the nucleus determines where the bonds form between adjacent atoms, so that determines the arrangements, the three-dimensional spatial arrangements of the atoms when they stick to each other, when they bond to each other, okay? All right, so as an example, let's look at, say, carbon. So here we have the nucleus of the carbon atom, all right? And it's going to have in the outermost shell 4 electrons. Remember, carbon has an atomic number of 6. So 2 electrons in the first shell, 4 in the second or outermost shell. That means it can form 4 bonds. Now, where are those electrons in the outermost shell found? They're found in 4 orbitals. And if you have your nucleus there with your neutrons and protons, you'll have one orbital here, you'll have a second orbital there, a third here, and then 1 sort of going back into the plane of the screen three-dimensionally. So these are where the outer shell or valence electrons are found. So these orbitals, as you see here, take on these sort of teardrop-shaped three-dimensional volumes of space, and that's where those electrons are kind of restricted to. You can sort of think of those electrons as being located in sort of around all 4 corners, I guess you could say, of the nucleus of the atom. They're still attracted to the protons in that nucleus, but they're as far away from each other as they can possibly be. Okay, and as we'll see in a little bit, chemical bonds can only form where the orbitals are. And that is the key to understanding three-dimensional shapes of molecules that are built from atoms. Okay, so atoms with incomplete valence shells can share or transfer valence electrons with certain other atoms. And again, the whole point here is always to complete their outer shells and become less reactive and more stable. These chemical bonds, these interactions usually result in atoms sort of staying close together, held together by attractions, and those attractions are called chemical bonds. And there are various different types of these chemical bonds, as we'll see. First type we're going to talk about, excuse me, is what's called a covalent bond. Okay, covalent bond. Co means to share, and valent refers to valence electrons or outer shell electrons. So a covalent bond is the sharing of a pair of valence electrons by 2 atoms. Now, in this bond, the shared electrons count as part of each atom's valence shell. And because of that, when the atoms come together and share electrons, they're actually helping to complete each other's outermost or valence shell. And that's sort of what you see going on here. So imagine we have 2 hydrogen atoms right here. You can see the spherical space, three-dimensional space or orbital where the electron is found. Well, these atoms have the positive proton, which is keeping that negative electron in check or in space around it. And let's imagine that they sort of start to just randomly drift closer together. The electron around this atom, while being attracted to that proton, can also start to become attracted to this proton. After all, it's a positive charge. The electron here can start to become attracted to that proton. You see how the orbitals are sort of becoming maybe egg-shaped? Okay, and that will pull the atoms together, and they'll eventually reach a certain distance apart where they stop, and now you can sort of think of both electrons as kind of doing a figure 8. It's really not that way, it's not that simple, but it helps to think of it that way. But now, the idea is that because the electrons are moving at the speed of light, at any given millisecond, both electrons are here, and the next millisecond they're there, and then here and there. So it's sort of an averaging effect. At any given millisecond, each nucleus now has 2 electrons around it, so its single or outermost shell is effectively complete. Remember, that first shell can hold 2 electrons. Okay, so I have a video or animation to show you this, so let me play this, and this will help you understand why it is that these 2 hydrogen atoms bond together in a covalent bond by sharing a pair of electrons.
A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
Okay, so the animation there mentioned 2 terms that are very important. One I've already defined. Talked about compound in the first part of this video lecture. A compound is a substance consisting of 2 or more atoms of different elements in a fixed ratio. So water, for example, that you see here, H2O. A molecule is the term molecule rather is a more general term. It just defines 2 atoms of any type that are bonded to each other. So for example, where we have water here, okay, you could also have N2. That's called molecular nitrogen. That's not a compound because it's not 2 or more atoms of different elements. They're both nitrogen. But it is a molecule. Okay, both of these, the water you see here and molecular nitrogen, are molecules because the definition for molecule is just 2 atoms of any type bonded to each other. 2 or more atoms of any type bonded to each other. Okay, so in this example with water, what we have is 1 covalent bond here and a second covalent bond there, okay? Those are both single covalent bonds. But what if you had 2 carbons, for example? So this carbon with a double bond to that carbon. That double bond that you see in the center represents 2 pairs of electrons being shared between 2 atoms. So it's 4 electrons being shared. Sometimes you'll see double bonds quite often. Less often you might actually even see a triple bond between two carbons, but probably not in most of the molecules we're going to talk about. Excuse me. But if you take organic chemistry, you'll see that probably fairly often, actually. Okay. So what I've shown you here, an example with carbon, for example, or right here with water, that's what's called a structural formula. So for example, let's say we have H2. Well, if I write it as H2, that's referred to as the molecular formula. We can also, however, show it as a structural formula, which shows 2 atoms of hydrogen with that single covalent bond attaching them to each other, okay? These are just 2 ways to depict molecules and compounds and that sort of thing. What you see here is a figure from the textbook that kind of shows this, plus a few other ways of depicting molecules and compounds. Here we have molecular hydrogen, so H2, 1 hydrogen there, 1 there, bonded by a single covalent bond, as I showed here. That's the structural formula for it. This is called a Lewis dot structure. You see that more often than not in chemistry textbooks. You don't really see it so much in biology textbooks. It actually shows you the 2 electrons there. It looks like a colon, but it's actually 2 electrons. This is called the space-filling model. It shows you 3-dimensionally what it would look like if you could actually see it. These are all useful in their own right in various different aspects of understanding chemical structure and that sort of thing. But what we typically see in biology is either the electron distribution diagram showing you where the electrons are, the structural formula, or the space-filling model. Now look at molecular oxygen. So here we have O2, right? So remember, oxygen has an atomic number of 8, which means 2 electrons in the first shell, 6 in the second. So it needs 2 electrons to complete its outer shell. Let me zoom in on this a little bit. And if you look at this oxygen on the right, there's 2 electrons in the first shell. We have 2, 4, and then let's say this pair is 6. Those are the electrons that this oxygen brought to the party. These 2, 4 here, and 6 there, plus those 8, or those 2 for 8, are the electrons that this one brought. So they're sharing these 2 pair of electrons. Now, in your mind's eye, block out this oxygen on the left, and you see that the one on the right has 2, 4, 6, 8 electrons in its outer shell. Block out this one in your mind's eye, 2, 4, 6, 8 around in the outer shell of the oxygen on the left. So you can see that both of those atoms now have complete outer shells. All right, water. Water is H2O. Let me zoom in on that one. So why is it H2O and not H6O, for example? Well, remember, oxygen only needs to bring in 2 atoms through covalent bonds because those 2 atoms would supply it with the additional 2 electrons it needs to complete its outer shell. Okay? All right, and you see it gets that by bringing in 2 hydrogens. So block out this hydrogen and that one. You get 2, 4, 6, 8 electrons around the oxygen. Block out the oxygen, you have 2 around hydrogen. First shell's complete at 2, 2 around this hydrogen. So everybody's happy, basically. Now look at methane. Methane is CH4. Carbon has 6 electrons, 2 in the first shell, 4 in the second. Its valence is 4, needs to bring in 4 atoms, so it forms 4 bonds. That's why that's why it's referred to as CH4, right? H4, 4 hydrogens. Each hydrogen brings in 1 electron, block them out, 2, 4, 6, 8 around carbon, so its outer shell is complete. Block out the carbon, you see there's 2 here, 2 there, 2 there, and 2 there. So all those hydrogens are now complete. Everybody's happy. Okay. Now, notice that in water, for example, and I forgot to mention this a minute ago, in water you have 2 bonds, one here and one there. But we have 2 other pairs of electrons in the outer shell that don't participate in bonding. They're called lone pair electrons, okay, lone pair electrons. They would tend to push this hydrogen that way and this hydrogen that way, and that's why the molecule looks like that. It's why these hydrogens come off at this sort of weird angle. They're not straight across from each other, all right? That shape, because of those lone pair electrons, gives water some of its life-supporting properties. Now look at methane. Methane is CH4, and I showed you before that around carbon you have 4 orbitals in that second shell, and they're at all 4 sort of, quote, corners of that carbon atom, and where those orbitals are is where the hydrogens can bond. And that's exactly what you see right here. 1 hydrogen, a second, 2 that sort of sweep backward into the plane of the screen, but you can tell that those hydrogens are as far away from each other as they possibly can be because the electrons of this hydrogen carbon bond are repelling those of this one, which are repelling these, which are repelling those. So that carbon then has that 3-dimensional shape. That shape that you see there is called a tetrahedron. It's a very common shape in organic chemistry and biochemistry when you have carbon involved, and you're going to see that quite a lot this semester. Okay, so we've talked about bonding capacity. Bonding capacity is related to valence in the sense that valence tells you how many electrons an atom needs to complete its outer shell. That also tells you how many bonds it can form. So bonding capacity and valence are the same thing. All right, moving on to another topic here. So still within chemical bonding, but moving away from covalent bonds. So we talked about covalent bonds as an attraction between 2 atoms where they share electrons. We're going to get to a couple of other types of bonds here in a moment. Before we do that, we need to talk about a peculiar feature of some atoms called electronegativity. Okay, electronegativity. Electronegativity is an atom's attraction for the electrons in a covalent bond. The more electronegative an atom is, the more strongly it pulls electrons, shared electrons, toward itself. Okay. Now there are a couple of atoms on the periodic table that are extremely electronegative. We have oxygen, nitrogen, and fluorine, for example. Now, fluorine plays no role in biology, so we don't really care about it. But oxygen and nitrogen certainly do play a role in our biology. They're 2 of the CHON elements that make up 96% of living tissue. Oxygen is the strongest in terms of electronegativity of those 2 atoms, okay? And this is a really important feature of the atom that imparts some life-giving characteristics to water molecules and plays a very important role in biochemistry, as we'll see, okay? All right, so let's imagine that we have let's say we have, let's just do a water molecule. So we have oxygen there, you have hydrogen here, and a hydrogen there. Remember, you have a lone pair here and a lone pair of electrons there, okay? All right, so we have a pair of electrons being shared here and another pair there. That's a covalent bond. But that oxygen is highly electronegative, much more so than hydrogen. That means that the electrons of the shared bonds are actually being pulled toward the oxygen atom. And remember, electrons have negative charge, right? So it's like the oxygen is pulling negative charge toward itself, and that gives the oxygen side of the molecule a slightly negative charge and leaves a slight positive on each of the hydrogens. Okay, so that situation I've just shown you, where you have a molecule or a compound like water that has a partial negative side and a partial positive side, that's a situation referred to as polar. If I tell you something is polar, that means that one end of it or one side of it has a positive charge and the other end or side has a negative charge, all right? So we have covalent bonds here between hydrogen and oxygen and water. And specifically, they are referred to as polar covalent bonds. Because, for example, this end of that polar covalent bond is positive and that end is negative because the oxygen, being electronegative, is pulling those shared electrons toward that end of the bond, giving that side of the water molecule a negative charge and leaving a positive here from the proton in each of the hydrogens. Polar covalent bonds. But what if we had, say, two carbons with a single bond between them? Well, carbon has a certain amount of electronegativity, but the point is that here you have two carbons, so each of those atoms has exactly the same electronegativity. They're exerting exactly the same pull on that shared pair of electrons, so that bond is called nonpolar covalent. Nonpolar covalent, okay? All right, now, if we look at the water molecule, this is what we see in a much nicer drawing than what I did. So again, we have our oxygen here, which is electronegative. We have a pair of electrons there, a pair here in these covalent bonds, but they're being pulled toward the oxygen, giving it a partial negative charge. A little squiggle right there, that's the lowercase letter, Greek letter delta. In chemistry and biochemistry, it means partial. Partial negative charge, leaving partial positive on this side. So the water molecule is polar, and that is critically important. If water weren't polar, we wouldn't care about it because we wouldn't be here. There'd be no life on this planet because water wouldn't support life. And we're going to see all about that in the next chapter, chapter 3. Okay, now let's move on to another kind of bond. We'll get back to electronegativity as it relates to what's called a hydrogen bond in a minute. But before we get to that, let's talk about what's called ionic bonds. All right, ionic bonds. So here we have another kind of chemical bond, but again, this is just a different way for atoms to gain electrons, for atoms to complete their outer shells, I guess is more accurate to say. So in covalent bonds, we talked about atoms sharing electrons. That's not what happens in ionic bonds. In ionic bonds, you have an atom that can strip electrons from its bonding partner, actually steal electrons, not share them. Great example is the transfer of an electron from sodium to chlorine. So we talked about table salt, NaCl, at the very beginning of this video lecture, or the first video lecture for this chapter. And I showed you how sodium explodes by itself and it's reactive, how chlorine's nasty, but you put them together and you get table salt, right? Well, the bond that holds sodium and chlorine together, and again, that's NaCl, is an ionic bond. Okay, so what happens here is that we have sodium actually losing an electron to chlorine, not protons, just an electron. And normally sodium has the same number of electrons as protons, and the charges cancel out, and the atom does not have a charge as a result of that. Same is true in chlorine. But the sodium is going to lose an electron to chlorine, and that is going to mean that sodium now has one less electron than it does protons. So the sodium becomes positively charged. The chlorine gaining that electron now has one more electron than it does protons, so it takes on a negative charge because electrons are negative. These charged atoms are called ions. Okay, they're called ions. So let's take a look at why this happens. So here we have sodium. If you go back to the periodic table, you'll see sodium has an atomic number of 11. That means it has 11 protons, 11 neutrons, and 11 electrons. And with those electrons, you see we have 2 in the first shell. We have 2, 4, 6, 8 in the second shell. That's 10. 1 left over for the third. And that third shell being able to hold 8, but only having 1, is why sodium is so reactive. Chlorine has an atomic number of 17. 2 in the first shell, 2, 4, 6, 8 in the second, that's 10, 7 in the third. So its third shell, outermost shell, valence shell, is almost complete. Just needs 1 electron. Well, go back to sodium. Is it easier, do you think, for sodium to lose 1 electron or gain 7 in order to complete its outer shell? Easier for it to lose 1. Chlorine, easier to lose 7 or gain 1 to complete its valence shell. Easier to gain 1. These two atoms are a match made in heaven. All sodium has to do is transfer that 1 electron to chlorine. It goes back to a complete outer shell, a second shell. Chlorine gets its third valence and valence shell complete. But again, now our electron and proton number is different. Here you have 10 electrons, 11 protons, so a positive charge. 1 proton's positive charge is not canceled out, so it becomes a positive, what's called a cation, a positively charged ion, sodium. Chlorine takes on that 1 extra electron. Now it has 18 electrons, only 17 protons, so it becomes a negatively charged ion, an anion. And what do opposite charges do? They attract. So these two atoms stick together, sort of like static clinging, essentially, through opposite charge attraction. But it's caused by an electron transfer, which then converts them both to oppositely charged ions, which is then why they stick together. And that opposite charge attraction is the ionic bond. Okay, so let's take a look at another animation for this.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion. In this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, so sodium chloride is what we call an ionic compound. It's composed of atoms that are bonded to each other through ionic bonds. Salts are ionic compounds. There are various different kinds of salts. Sodium chloride is one. You have calcium chloride, potassium chloride. But the point is they're all formed by ionic bonds between the atoms that you see in those compounds. They generally form crystals, for example.
Sometimes atoms...
That's exactly what and that's what you see. Well, I must have gotten rid of that slide. If you look at a crystal of salt, for example, you see it's sort of shaped like a cube. A single crystal is. And that's because of the very regular arrangement of the sodium and chlorine atoms that are ionically bonded to one another. Okay, so ionic bonds are relatively strong, but they're not as strong as covalent bonds. Okay, covalent bonds are the strongest. Then you have ionic bonds. Next, we have what are sort of referred to as weak chemical bonds. Okay, there are some people who refer to ionic bonds as weak chemical bonds, although they're not as weak as the next kind of bond we're going to talk about, which is definitely a weak bond. It doesn't really matter. Covalent are the strongest, then you have ionic, and next we're going to talk about the weakest bond that is really important for biology. So most of the strongest bonds in organisms are covalent bonds that form a cell's molecules. Okay, we're going to see quite a lot of that throughout this course. But the weak chemical bonds, even though they're weak, they are very, very important because they generally help to lock in the overall shape, three-dimensional shape of molecules. And one thing I haven't mentioned yet is a very common theme throughout biology and chemistry, and that is the theme that we refer to as structure and function. Structure and function. So what this means, refers to, is the fact that, particularly in the case of biochemistry, the structure of something like a compound, a molecule, imparts a function to it. Things get their function from their structure. DNA does what it does because of its structure. Protein molecules in particular do precisely what it is that they do because of their three-dimensional shape, because of their structure. That's why understanding all this stuff about atoms that we've been talking about, why they bond together, why they're reactive based on electron configuration, all that, that's why that's important, because if you can understand that stuff about atoms, you can figure out why they stick together in the three-dimensional arrangements that they do, and those three-dimensional arrangements of those atoms then determine the function of the molecule, and the function determine the structure of the molecule, and the structure then determines the function. Okay, so what we're going to talk about next is the hydrogen bond. The hydrogen bond is really important. It's a very weak bond, but they can be super abundant, especially in water-based solutions, okay, like what we see in our bodies. So I'm going to read this definition for a hydrogen bond, then I'm going to show you an image which will help you understand it, because the definition probably isn't going to make a lot of sense. Then I'll come back to the definition and read it again. So a hydrogen bond forms when a hydrogen atom that is covalently bonded to one electronegative atom is also attracted to another electronegative atom. All right. In living cells, the electronegative partners are usually oxygen and nitrogen, as I talked about before. So let's go look at this figure here. Oops. I've lost my figure. Okay, what I'm going to have to do is draw this. So here we have a water molecule, right? That's water, okay? And remember that we have positive charge here, positive charge there, and negative charge there. Let's imagine also, excuse me, that we have an ammonia molecule. Now ammonia is NH3, okay? So we have a nitrogen atom there, and then we have, I shouldn't probably do that like that. Let's see. Let me just erase that real quick. All right. Okay, so let's say we have our nitrogen atom, then we have 3 hydrogens, okay, like so. Now, nitrogen, as we said, is also electronegative, if you recall. So it's pulling the electrons of these covalent bonds here, here, and here toward itself, giving it a slight negative charge, leaving positive charge on those hydrogens again. Okay, that's a positive, not an H, sorry. Okay, what we have then is a bond shown with dotted lines. Hydrogen bonds are always shown with dotted lines right here between the nitrogen and the hydrogen. They're oppositely charged, right? Positive, negative. Okay, that's our hydrogen bond. So let's go back over that definition. A hydrogen bond forms when a hydrogen atom that is covalently bonded to one electronegative atom. So we have a hydrogen atom covalently bonded to one electronegative atom. That hydrogen atom is also attracted to another electronegative atom. That's our hydrogen bond right there. And again, they're always shown as dotted lines to sort of indicate that they're weak. They're weak chemical bonds. All right. Okay. So hydrogen bonds are superabundant in water. They're superabundant in what we call aqueous solutions, solutions where water is what's doing the dissolving. Your blood, for example, the fluid inside your cells, those are all aqueous solutions. But hydrogen bonds are superabundant in those. And they can be very abundant in proteins, DNA, sugar molecules as well. And they're responsible for sort of maintaining shapes of these molecules. All right. Okay, so next we're going to, that's kind of the end then of the bonding part of this chapter. And actually I can see I'm not going to get done with this in the next 10 minutes, which would make it 45, so I think I'm going to go ahead and stop here, and then I'll come back and finish up the last bit of this. So we're going to have 3 video lectures for this chapter, but that's okay. So let's go ahead and stop here, and I'll